it's my pleasure to introduce Blake to Warwick. So Blake is a postdoc at Harvard Mathematical Sciences and Application Center. He recently completed his PhD in applied maths at Harvard. His research sits in the intersection of machine learning, statistical physics, and theoretical neuroscience, bringing together the ideas from these areas to better understand learning systems. Before graduate school, Blake studied physics, engineering, and computer science at Washington University. Please join me in welcoming Blake.
Hello, everyone. Thank you so much to the organizers. This has been a lot of fun, and thanks, MUFON, for setting up the second tutorial. I think I can reuse a lot of the same notation and ideas. So I'm basically going to talk about disordered dynamics in high dimension. And the idea is based on a lot of my examples that I'm going to provide are going to be based on this technique or idea that came out of the spin glass physics in the 80s and 90s, known as sort of dynamical mean field theory. And what we're going to try to build toward is we're going to start with some simple models, and we're going to try to learn the method. Well, actually, first, before that, I'll give a couple of just historical examples where there's been some success in understanding disordered dynamical systems in high dimension using this method. And then after the history, I'll give some various toy models where we can do some calculations and learn how to use the method, more of a tutorial. And then near the end, I'll talk a bit more about how we've applied this in some recent deep learning theory papers and some new results on understanding the weight spectra of neural networks in this infinite width feature learning network regime. Okay, so to start, I'll just give maybe a bit of history. So some three just quick examples where I can point out some success with this DMFT method. So one was, I mentioned this idea of spin glasses. So in a spin glass and in a long range extended spin glass, you have a state S. So S, sometimes it's binary, but I'm going to take it to be on the n sphere. So in dimensions, but confined to the sphere. And the idea is there's some kind of random Hamiltonian. And the random Hamiltonian depends on couplings between many sites. So I'm going to look at a particular spin glass called the P-spin model. And there's basically a tensor that's completely symmetric, J, I1 through IP. And this couples interactions between spins at P different sites, SI1 through SIP. And the constraint is that I'm on a sphere, but the sphere is of radius square root of n. So I want the typical spin to be of size 1. Okay, and so the statics of this model, so people first were studying sort of equilibrium distributions for this model. And it's sort of an interesting object because if for a given realization of this object J, you can define the partition function for this at a finite temperature as some integral over the sphere of ds e to the minus beta h of s comma j. So for a given realization of a random j, this measure itself, the Gibbs measure itself, is a random variable. But you'd like to compute sort of typical expectation values of observables of s, so functions of s, against this measure. That turns out to be kind of challenging, because if you just write down, let's say I have an observable O of s, and I want to average it. Well, there's two levels of averaging. I can do the average of s given j, which is this distribution, defined by this Gibbs measure. And then I can also average over the j itself. So this would look like 1 over the normalization factor right? So this inner thing is the average over s given j, and then we have this outer average of j. But this is kind of complicated because this denominator has a z. So this motivated a lot of kind of interesting tools and techniques, including the replica method and other ideas from statistical physics. But the replica method, for example, requires a couple of weird things. I mean, so it's not completely rigorous. The idea is you take integer moments. So you imagine you have n little copies of this z object. You try averaging them over j. And then you have to make some kind of structural assumption to figure out how to take this integer n to 0 continuously somehow. So you have to make some kind of structural replica symmetry ansatz. And then once you do something like this and take n to 0, this should go to the average of log z, which is your free energy. This is ultimately what you want. This is weird for a number of reasons. One is that you're doing this weird analytic continuation. One is that the other bigger physical problem is like, in some sense, some systems may not actually, if the Hamiltonian is complicated enough, some systems may dynamically not actually reach equilibrium in reasonable amounts of time. So this motivated a different method. So a couple of names associated with this was, let's see, I gave some examples. Okay, Crisanti, Horner, Summer. And another one is Cugliandolo and Kirchhoff. These are both 1993. And the idea is here, instead of studying this sort of equilibrium configuration, you think about dynamics on spins. So yeah. Oh, right, a little larger. Okay, yes. So you consider dynamics on states S. So I'm going to have one term that this lambda of t is a Lagrange multiplier that's going to enforce this spherical constraint. Let's just write it element-wise. I'm going to have one term that's a gradient, effectively, on my energy. And then I'm going to include Brownian motion. I'll call it like epsilon of t. So this is Brownian motion. So and it's epsilon of t, epsilon t prime. T minus t prime. Okay. So right. So people were instead interested in these kinds of Langevin dynamics on this energy function. And an interesting result is that okay, I dropped some normalization factors. So like if you want this to be scaled properly, you need something like a factor of n here, and then like a factor of maybe p factorial, just for counting reasons. But the point is that the DMFT idea is something like the following. When I consider the typical behavior of this system at large n, I can, instead of thinking about a very complicated coupling between all these nodes through this like p-spin hypergraph, I can replace this finite n picture as n goes to infinity with a the behavior with basically an integro differential equation that defines the behavior of a single site. This single site takes in a noise process that's colored, so it's a Gaussian noise that has correlation statistics across time, and integrates some history-dependent version of itself. So this is S of t, and then produces some output. So I'll define exactly what you mean. So this is before averaging, and then I take n to infinity. The claim is you can replace this system with an equation for a typical representative spin in the system. So like one variable stochastic process. Okay, you'll get, there's some counting, p minus 1. Plus the noise. Okay, and this noise has a covariance that's given by an object C, T prime. Okay, so what did we do? So the claim is I can replace this coupled system in n dimensions with a non-Markovian single site equation. The single site equation is driven by a colored noise process, and it introduces a non-Markov, S of t prime. This is C T prime with p minus 2, S of t prime, and then the noise, basically. Okay, so notice S only interacts with itself. It's not interacting with any other nodes. But the consequence of characterizing the interaction with all the other nodes is taken care of by this we're going to call this an Onsager correction or a response term. There's a lot of terms for this. But the point is these R's and these C's govern the behavior of the network, because the C governs the behavior of this random variable. And the C also shows up in this formula for this self-interaction.
Oh, sorry.
Yes?
Sorry, is that meant to stay on the sphere?
Right, sorry, what's up?
Yes, because, sorry, I was just making sure I'm getting it right. So it's meant to be the up, down, is meant to stay on the other side.
Yeah, so let me define how to do that. So what we want is, what you could do is you could look at S of T. So my claim is that averages of this single-site stochastic process recapitulate averages over the measure of the entire population. And so the spherical constraint is that the average of the square of S at equal times has to be 1. So what I can do is I can choose lambda so that ddt of the average over this process. And what does this average mean? It means averages over this psi and this epsilon. Those are the two sources of noise. So if I average this, I have to get 0 first derivative. So I choose lambda. I choose lambda of t so that happens, which I'm free to do. But the point is that these kinds of averages become deterministic as n goes to infinity, because these kinds of empirical measures are converging. So that's the claim. Okay, so that's just a historical example. One interesting thing about this is that there are regimes of this temperature beta where the equilibrium calculation and the dynamics calculation give you different kind of results. So let's say I take one system here. This is taking this is taking in the number of sites to infinity first. And if I take first sort of n to infinity, and then I look at this correlation. Oh, maybe I should define correlation response. Sorry, this is the key thing. So the correlation function CTT prime here is the average of this S at time t with this S at time t prime. Okay, and the response is, it's the result of what would I get if I kicked the right-hand side of this equation at time t prime and measured the response for the same spin at time t. So that's ds of t with respect to, we could kick, for example, this variable. Okay. And so these are both averages over this stochastic process. Okay, so this correlation kind of, you can interpret it as how fast is the system decorrelating? How fast is it kind of like decorrelating from itself as t and t prime change? R is like how fast do I forget perturbations? So it's also measuring kind of how quickly you're decorrelating. At equilibrium, these R's and C's are related by a fluctuation-dissipation relationship. Non-equilibrium, they don't have to be. Okay, so one result that's sort of interesting for certain beta, so there exists some betas for where, imagine I take the system size to infinity. I look at t plus tau. So I wait a very long time, t. So I let the system kind of relax for a long time to some configuration. And then I ask, okay, so I've waited a long time. The system should have forgotten maybe about its initial conditions. And then I ask about how quickly it forgets or decorrelates. So I take then tau to infinity. You can dynamically show that this thing can be positive. But if you did the equilibrium calculation, which is the other order, that would be like taking t to infinity first, c of t, t prime, then taking, or sorry, t plus tau, and then taking n to infinity. You could do tau too, somewhere in here. This is equal to 0. So there's a paramagnetic equilibrium phase, but in practice dynamically, it could take exponentially long with respect to n to actually escape and get to the equilibrium configuration. So in a really large system, you'd have to wait a very long amount of time to actually kind of escape. So there can be, the point of this is just that dynamically the physics can actually be different in principle. Not always, but it can. So that motivated some of these things. All right, so now I'm going to just do one more, maybe quick historical example. Okay, which is the case of a random recurrent neural network. And the key citation here is Sampolinsky, Crisanti, Summers, 1988. Okay, so the model here is I have a recurrent network. It has a kind of leak term, so if there were no inputs, the system would decay to 0. But then there's some recurrent connections, Jij, phi of Hj. And the key thing that separates it from the previous example, so the previous example is all about equilibrium, or like all about kind of sort of optimizing this the spin glass Hamiltonian, this energy function. But you can imagine that I could have physical systems where Jij is random, but asymmetric. So there's no there's no constraint that, so in general, Jij is sampled independently from Jji, so they don't have to be the same. Okay, in this kind of model, there's no energy function that I'm optimizing, so I have no hope to kind of appeal to equilibrium physics to make any kind of statement. But it would still be nice if I could like understand properties of the dynamical system here when the system becomes large. Okay, so the same kind of thing happens, and I'm gonna, in a minute, we're gonna do some like in detail calculations, but I just want to state the same kind of result. In this process, basically, I can just replace the in-neuron system, which was like my, here's my recurrent neural network with all the couplings. I can replace this with a single site picture where I have a random variable chi, or psi of t, and that comes in, and then I apply some linear filter and get some output h of t. So there's no response or feedback term in this model. So what is the equation for this? I have basically a single site equation. I'm just going to move this over. So 1 plus the derivative of h. So this is a typical neuron in the network. It's just equal to a random process. And this is kind of what you'd more or less guess. You'd say, hey, imagine that this thing just has, at large n, central limit theorem behavior. So this thing has a variance, and this thing has a mean. The mean is 0, because Jij is 0. And there's no, well, there's no response term. I'll talk about that in a minute. But the variance of this guy is basically independent across neurons, but it's correlated across time. So like, what's the statistics of psi of t? It's going to be c of tt prime. And what is c of tt prime? Or I'm going to call it c phi of tt prime. This is the average value of this nonlinear activation for h at time t, and this nonlinear activation for h at time t prime, where h is drawn from a distribution that we got from this dynamics. So if I knew psi, so psi is this Gaussian process. If I knew the covariance statistics of psi, right, that I could integrate that and figure out the covariance statistics of h, right, and h would be Gaussian. It's just a linear filter of this psi variable. And then if I knew the covariance statistics of h, right, so h is a GP with a covariance c sub h. If I knew the covariance c sub h, then I could do this 2-point average, and I could get c phi, which is the covariance of this. So it's a sort of self-consistent equation. Okay? And one thing that's interesting is that even though this thing doesn't have an energy function, it can still have an interesting kind of long-time behavior. So people were interested in imagining this system, taking first this n to infinity limit, you get these equations, and then asking about, are there ever solutions or states for this correlation function that persist at long times, even in the absence of drive, even in the absence of external inputs. And remarkably, there's a regime where this maintains non-zero activity, maintains chaotic behavior, but even in the absence of inputs. And so here's kind of a result. You can look for a certain ansatz. So something you can do with these kind of DMFT equations is you can look for a certain kind of guess for a solution. So one guess you could look at is a time translation invariant, or TTI ansatz. So this would be, I approximate or look for a solution for CH and C phi that are just functions little c of tau, where tau is the time lag t minus t prime. So functions of one variable. So the idea here is that after enough time, I should forget about my initial condition. Absolute time doesn't matter, and I just care about relative times, t minus t prime. Okay, it turns out now this equation, right, I can write down a general equation, right, for the two-time correlation. So ch t prime. This should be equal to g squared. Oh, sorry, there's a g squared here. This gain factor g is important. G squared times this c phi function. But c phi is just a function of this. It's a functional of this other covariance ch. So, okay, so this is the general thing. And then under this TTI ansatz, I'm just assuming that everything's a function of tau. So this just becomes a second derivative like this. Little c of tau equals some function f of c of 0 and c of tau. Okay, and I'll define what it equals g squared. Okay, does this make sense? And what is f? F is f of c0, c of tau, is the average of phi of h, the average of phi of h, let's say phi of h prime, where h and h prime are Gaussian with 0 mean and covariance C0, C of tau, C of tau, C0. So the idea is, when I'm at equal times, the covariance is C of 0. And when I'm at a time like tau, the off-diagonal covariances are C of tau. Right? So this is just, this right-hand side just becomes a function of C0 and C of tau. OK. So now imagine I know C0. Imagine I fix C0. Does anyone have a sense of what kind of differential equation this is? Imagine I'm just in like first year physics. Does anyone have a sense of this? Oh, it's close. I mean, so it's even simpler than that. So like, think F equals ma. It's just Newton's law, right? So this is like an acceleration. This is like two derivatives. And then the right-hand side, if I move this c over, it can be viewed as a gradient of a potential on c, right? So there's an interpretation where you say, OK, well, I can define some potential v, which is minus 1/2 c squared plus g squared times this f, times some, OK, I need an antiderivative of f, basically. So define phi as the integral, as the derivative of some psi prime of z. Then this equation would be the average of psi h prime for h prime. Okay. So the point is, you get some kind of potential, and you can plot this potential for different C0. You could choose an offset point, right? You're free to choose an offset point so that when you evaluate this at C0, when c equals C0, you get 0. You choose the convention that V0 sub C0 is equal to 0. Okay, so you could plot this, and it looks like this. Okay. And Newton's law also has a conservation of energy, right? So we have an energy function that's like 1/2 dt d tau of c squared, and then plus this v of c sub c0. Okay, so everything seems fine, except we don't actually know this value c0. How do we figure this out? Well, we can figure that out by conservation of energy. So we can look for a solution where at long time I decorrelate. So c dot at time infinity is 0. And we also chose that v of 0 is 0, right? So when I'm completely decorrelated, I have zero potential energy. So epsilon has to, so the total energy has to be 0. And that actually fixes the equation that for C0. So VC0 is C0. So you now have a kind of self-consistent equation for this boundary point. And then what is the Newton's law telling you? It's just telling you start with, your solution starts like a ball rolling down this hill, and then it ends up at 0 right at time infinity. So that's the dynamics of your system. And you can plot the autocorrelation function. And it's some nice smooth curve, tau, as a function of c of tau. So, OK, this is just to say, what's the high-level story? The high-level story is we had a complicated coupled system. We replaced it with a single-site stochastic process that was driven by a colored noise. We were able to study the behavior of this system at long times using this TTI ansatz. And even though the system never equilibrates, there's a long-time behavior of the autocorrelation that you can capture. OK, so that's another success story. I was going to do one more, which is kind of signal propagation. Oh, yeah, go ahead. I'm going to do an, so I haven't taught anything yet. So this is a tutorial, and I haven't taught anything. I'm just sort of flashing results about interesting things. And I'm just sort of saying, you can say all sorts of stuff using this DMFT about like the Lyapunov spectrum, how chaotic this system is. You can compute a lot of cool observables. I'm just trying to get you excited about this concept. Now let's actually do maybe a tutorial. So I was going to do one more even history thing, but Mufon talked a lot about signal propagation, so I think that's OK. OK, so let's learn the method with a simple example. Yeah. OK. So I'm going to introduce this through just like linear dynamical systems. OK. And so in a linear dynamical system, I'm going to imagine I have some state h of t. And I'm going to imagine that it's evolving according to a linear system where there's a random matrix M acting on H. And then I could add some kind of like some inputs to the right-hand side if I want, okay? And you can put different choices of M here, and you'll get different kinds of behaviors. So the first model that we're going to do is a GOE or a Wigner matrix. Okay, and this is a matrix where Mij is equal to Mji, so it's symmetric, but each entry is sort of normal with mean 0 and variance 1 over n. Okay, that's the first thing we'll look at. Then we'll look at a plus a spike or a collection of spikes. So we'll talk about how to deal with that. And then we'll do a simple linear regression problem. So we're going to study linear regression in a joint limit where the data points p and the dimension of the features n are both diverging with an aspect ratio p over n that's alpha. So that should feel somewhat similar to this idea of a proportional limit, but just a proportional limit for data in a simple linear regression problem. And then I'll do a quick aside about the random feature extension of this, random feature model extension of this. And then after we do some of those simple random matrix models, I'm going to try working up to basically some kind of theory of, so then we're going to do a kind of theory of infinite width networks, training dynamics plus, let's say, weight spectra. So has anyone heard of the BVP phase transition for outlier eigenvalues? So there's, in this toy model of spikes, we're going to have a very simple analysis of a spiked matrix and understanding when the spike generates an outlier and when it doesn't. I'm going to try to do something like that, but for weight spectra of trained neural networks. But it's a bit more complicated because the spikes depend on the random part in a kind of complicated endogenous way. So that's what we want to do. So let's do a very simple example. So let's start with a in-neuron system, or an in-neuron RNN, but it's driven by this GOE matrix. Okay, so I have d dt of hi is just sum over j of this Mij, and let's rescale m. Let's say that Mij is just 1 over square root of n times aij, where the a's are all unit variance. Okay, but a is symmetric, right? So times hj, and then I have this right-hand side ji of t. Okay. So now what I'm going to do is I'm going to imagine I have this in-neuron coupled system. Okay. Okay, and they all interact. Okay, fine. I'm going to add one new site to the system. Okay, and we'll call this new site h0 of t. Okay, and when I add this new site, so here was my old system. When I add this new site, it introduces a vector. What is this vector? This vector is, I'll call it a0. And it's the new coupling between h0 and all the other nodes in the system. Now, h0 has its own coupling, but it's of size 1 over square root of n. So I'm actually going to just throw that away. I'm going to pretend it doesn't end up mattering. Okay, but the point is, when I add this new site, it goes through actually a0 over square root of n. That's actually, each component has this typical size 1 over square root of n. So each of the nodes in the original system is going to be perturbed by a small amount. Each of them is going to feel a 1 over square root of n effect from this new site. What I'm going to argue is that these sites are going to have a small perturbation, but when I add up all the effects of the perturbation and the feedback back to h0, it's going to give me a correction. Okay, so that's the story. I'm going to try to justify it in a second. So the in-neuron system, I'm telling you that it's a weak correction, right? So h is going to go to some new h tilde. Okay, so this is a vector on the in-neurons in this system. H tilde is the new variable when I include h0. Because it's a small correction, I should be entitled to do some kind of like Taylor expansion or Volterra series, kind of around the initial dynamics. Okay, so this thing at time t should be like h at time t plus effectively a linear response. Okay, so I add up all the earlier times where I could have felt some response on the right-hand side. So when I added this new site, it's like I added to the right-hand side of this equation 1 over square root of n a0 times h0 of t, right? So this was effectively my perturbation. Let's just put this as vectors, sorry. A matrix, h vectors. Okay, so this is h vector. This is the Rn dimension. So this is the original system. So it has the old variables, it has this new perturbation, and it has this j. So it's like I kicked the perturbation, it's like I kicked the right-hand side of the system. So I could imagine taking a derivative of h with respect to j at an earlier time. And then what was the size of the perturbation on the right-hand side? It was this 1 over square root of n a0 h0. Yeah. Oh, yes. So do you want me to copy this again, or I'll write it? Okay. So.
I think on the other call we have like a recommended font size guide, which is now.
Okay. Yeah. Let me try that. Okay. So this is the new perturbed thing. The claim is it's like a linear response dh of t, dj of t prime. And then the scale of the perturbation I said was 1 over root n a0 h0 of t prime. Okay? And then plus higher order corrections, right? Plus corrections that are even more suppressed interwise, right? Okay, so these guys basically are just, they have this small perturbation. They effectively don't matter because this h was order 1 in terms of its own dynamics. But my claim is that this is going to feed back when I calculate how h0 is evolving. Right, so now I need an equation for h0. So d dt of h0, well, it's 1 over square root of n a0, right, dotted into the perturbed dynamics in the system, right, which was this h tilde of t. Okay, so let's expand that out. This thing is 1 over root n a0 dotted into h, the unperturbed system. So this was the dynamics before I added the new site, plus okay, is this legible? Okay, we're almost there. So now I'm looking at this new site, and there's one term that is a0 dotted into a vector that doesn't depend on a0, because it was just the dynamics of the system before I added the new site. So this should have a central limit theorem kind of effect. This is a sum of n random variables. They're all the a0s are independent in the ensemble that I was drawing them from. So this should behave like a Gaussian noise process. So I'll call this psi of t. And what's the correlation of this variable? So what's the cross correlation between this variable and itself at two different times? Well, it's going to be 1 over n h of t dot a0 h of t prime. Okay, but a0 is independent of h, right? So I can do this average, and this by construction is the identity, right? And so I just get h dotted into h over n. So that's my correlation function. So CTT prime is 1 over n h of t dotted into h of t prime. Okay? So that's this first term. So my claim is this first term is going to be a colored noise process, and it's going to depend on the cross correlation of the entire rest of the network, right, at pairs of time points. Okay. Now, what about the other term? My claim is the other term is not zero mean. It has a mean, and the mean of that term is order 1. But the variance is sort of subleading. The variance is 1 over n. So that basically, in words, this other term is going to concentrate. So let's argue why. So I have this 1 over n a0 dh of t dj of t prime a0, right? So what is this thing on average over a0? And remember, this was the expansion around the in-neuron system, so it doesn't depend on a0, right? So this is independent of this. So I can use the trace trick, right? I can just write this as a trace of a0 transpose times this matrix, this response matrix. Okay? And now this again is the identity, right? So this whole thing is actually just a neuron average like the correlation function, it's a neuron average of the single site responses. Okay, so what does this say? This says if I knew how neuron I responded to a kick in the right-hand side for neuron I at time t prime, and then I average that over the population, that's enough to calculate this, what I'm going to call the Onsager correction, this correction term from feedback. Okay, so what's at the end of the day, what did we get? We got the following description for H0. So we got the equation H0 looks like a Gaussian noise term that has correlation statistics that are given by C of tt prime. Then we had an integral of, I'm going to call this the response function. Okay. We have an integral over dt prime of the response times H0 again, right? And then plus we can add a J0 if we want. Okay. So this is the single site equation. Now what I want to do is I want to argue that actually this DMFT equation, even though it looks complicated, it's actually like encoding structure about the properties of this random matrix, including the spectrum of the random matrix. So let's do that really quickly. Oh, so two things to note basically. All the sites are actually going to now be distributed according to this law. There was nothing special about H0. I could keep doing this, and every site needs to follow this IID thing. So H0 only depends on its own independent noise, and it only depends on itself through its memory term. So none of the sites actually interact in this picture. So when I take n to infinity, it's like I have one stochastic process. And if I could calculate averages of the process, that closes the equations. So h of t prime averaged over this process needs to recapitulate c of t prime, which shows up in the statistics of this, right? And r I should be able to get by doing derivative of h with respect to, let's say, j. Okay? Because it's linear, you don't really need to average the response, but in general, yeah, you'd see that you have a population average of this response function. Okay? So the point is, this is actually a closed system, right? So if I know the initial conditions for the state h, its initial correlation, then I can actually integrate this forward, and it closes at the level of c and r. Okay? Yep.
So in the equation that you wrote, the first term is coming from the first term, the leading term there, and the second, the integral term is coming from the quadration term.
Exactly.
Like the J is both term coming from?
Oh, it's just, I don't really need it in some sense. But it's just, J was just my right-hand side fictitious source term that I could take derivatives of. So you don't need it. You could also just think about it as input derived to the system. But I could turn it off. So but the point is this, you're exactly right. This was the Kasai of t. That's what this term was. And this is that, this is going to become this integral of r times h. Okay. So for this matrix, does anybody know actually, like what is the spectrum of this matrix? Do people know what that is? The semicircle law. So let's see if we can get that from this equation. That would be kind of cool. Okay, so a quick thing is that, okay, what is the response for a linear system? Well, we said it was like 1 over n trace of dj, or sorry, dh of t with respect to a kick on the right-hand side at t prime. Okay, but h is just h, when we started the dynamics, h was just, m times h, right? Where m was a random matrix. So this is just 1 over n trace of the matrix exponential m of t minus t prime times kind of an indicator function, a step function, theta t minus t prime. This is the heavy side step function. So it's only non-zero if t is bigger than t prime. And if t is bigger than t prime, then it's the trace of the matrix exponential of t minus t prime. Okay? And so what would happen if I took so this reveals that r is actually, for the linear systems, it's just a function of t minus t prime, or tau. Okay? It's this. What would happen if I took like a Laplace transform of this variable, or let's say a Fourier transform? This would be 1 over n trace I omega plus m, or minus m, inverse, right? Or we can do, let's do a Laplace one, just so we're kind of on the real line. So, does anyone know what this object is called? Has anyone seen this before? For random, what's it? Stieltjes transform, resolvent, Stieltjes transform, yeah. So it's the trace of the resolvent of this random matrix. And okay, so this thing encodes, from this thing you can actually get back to the eigenvalues. So if you evaluate, let's call this R of Z. So if I plug in R of Z, where Z is lambda minus I epsilon, and I take 1 over pi of this, and I take epsilon to 0. From this actually function, I can get back rho of lambda. So that's like a nice property. So the point is this resolvent is encoding actually something about the spectrum, where rho of lambda is the empirical measure of where lambda I are the eigenvalues of M, basically. That's all I'm trying to say. Okay, so let's see if we can get the semicircle law from our response. So what does the theory say? It says take the equation for the response. Okay, so I need to compute the response function here. So let's do that. So I have this equation d dt of h of t is equal to some stuff. Let's compute the derivative of this function at a time, with respect to the right-hand side at a time t prime. Okay, so this is r of tt prime. Okay, and then it's equal to, so we're going to kick the right-hand side. So we're going to get 1, or like delta t minus t prime. And then we're going to get an integral here over r again. Okay, and yeah, so where did this one come from? This is taking a derivative of this term on the right-hand side, right? Okay, so this is now a nice integral differential equation for r. So I have that, and we also know that this is a function only of one variable. So d tau of r of tau is delta of tau plus r of tau minus tau prime times r of tau prime d tau prime. Okay, so what would happen to this kind of system if I took a Laplace transform? So what would I get if I took a Laplace transform of this? Does anyone know? So when I do a Laplace transform of a derivative, I can integrate by parts. So I do some like e to the minus zt tau. I do an integral against this. I could integrate by parts, and it'll give me a factor of z. Right, so this will give me z times the r of z, the Laplace transform of this function. The Dirac delta Laplace transform is 1. And then this is actually a convolution. And under the Laplace transform, a convolution is just multiplication. So this is r of z squared. Okay, so this is my claim. My claim is we just computed actually this r of z function, and this r of z function is the resolvent of this matrix. Okay, so we're close. We should be able to kind of calculate r and then do this trick, and then we should get the density of eigenvalues. So it's just a quadratic equation. So r should just be 1/2. Let me move the z over. So z minus or plus z squared minus 4. Right? Okay, so now I should be able to plug in lambda minus I epsilon. Oh, take the imaginary part. Sorry, that's important. Okay, so when is this going to generate an imaginary part? Well, it's only if z squared is smaller than 4. Okay, and then this is imaginary. So rho of lambda is only going to have some non-zero component if z squared is less than 4, and then if it does, so this will be like a ReLU, so it's only if this is positive, and then I need to divide by pi. And that's exactly the semicircle law, actually. So this is so what is this saying? This is saying that the eigenvalue densities, here's lambda, here's rho of lambda. They look like this semicircle that's supported between -2 and 2. Okay, so that's a very simple ensemble. Are there questions about the method or the idea at this point? Or
Sorry, like,
yes.
for clarity, could you use a different letter for the Statistical transform and the response?
Yeah. So like maybe G. So some people call this G of Z. So we call this G of Z for this, and then G of lambda minus I epsilon would be rho, which is this eigenvalue density. Yeah. Okay. And then I guess this should be G of Z. Okay. Let me be careful about this. Actually, you need to make sure to pick the branch so that. Okay, wait, yeah, that's. I guess the way I set it up, it's a minus sign. But okay, the point is that this is the row of lambda. You can. So I have some exercises in the notes where you can work through these things. But let's now do. So that's a very simple example where there's just one sort of shared space where all the random variables live in one vector space. What if there's kind of, I don't know, a more complicated matrix M? How do you deal with it? So I'm going to do one simple example, and then we're going to move on to actual neural networks. So let's say I have a linear regression problem. So I'm trying to learn. So my student is trying to learn a function 1 over square root of n. Let's call it w dotted into x, and my teacher is w star dotted into x over square root of n plus epsilon. So this is each data point has its own noise, and epsilon is just unit or variance sigma squared, let's say. Okay. And what I'm going to look at is I'm going to look at the gradient flow dynamics on W when I minimize not the test loss, but the training loss. So let me define two things. So one is what's the sort of expected value over any possible x, where x is just sampled from a isotropic Gaussian. So this would be, the test loss would be, what is the error between f minus y averaged over random instances of x from the population distribution. And this would just be 1 over n w minus w star squared. Okay. But more interesting is, sometimes you don't train exactly on the same data as you test on. You could have a finite data set. So let's say you have a data set that is a matrix X that is n by p. Okay. Where n is the dimension of the W that I'm training. And let's say that I'm going to look at the train loss, which is 1 over the number of data points p. Okay. So let's say I ran gradient flow on the train loss, and then can I use this method to track training and test loss dynamics as I do the gradient flow? So what I'm going to look at is I'm going to look at ddt of W is minus some learning rate that I need to pick, dl train of t d dw. Okay, so that's the gradient flow. And now my claim is that it's a bit easier to look at this variable. Let's call h as a vector w star minus w of t. So it's a function of time. And h's derivative is minus the gradient, or minus the derivative. If I took dl dh, it's minus dl dw. Okay. So the dynamics for h, you can show are just 1 over p x transpose x times h. Okay. So this is of the form that we were thinking about before, right? This is just a random matrix here. Okay, but now this is just a slightly more interesting matrix. So this is known as a Wishart matrix. And the limit where n and p diverge with p over n going to some constant alpha, it's known from random matrix theory that that gives you a well-defined ensemble that follows a spectral law known as the Marchenko-Pasteur law. So can we derive that from this? So I'm not going to go through the whole thing, but I'll explain how to do the cavity method for this model. So the trick is, you want to break everything up into each linear component in the random matrix. So you want to do what's called in random matrix theory a linear pencil. So one way to do this is to introduce a new variable, which is just what do I get when I do one application of x on h. Okay, we'll call that variable delta, where delta of t is defined as 1 over square root of n x times h of t. Okay, so now we're going to get a bipartite system. We have one space h that is n-dimensional, right? This lives in an n-dimensional space. Then we have this delta variable that lives in p dimensions. Okay, so how could you do a cavity kind of argument like what we just did, but for this system? So let's say I have h here. This is in Rn. Okay, and then I have my deltas. So here's delta. It's in Rp. So you do the same kind of cavity trick, but you do it two different ways. So the first way is over here. I can say, hey, let's add one node. So this is delta 0 of t. When I add this new node, that's like adding a new vector. That can perturb all the nodes on the left, all these n nodes. All their dynamics get perturbed. But then those perturbations feed back and give me a correction to delta 0. Okay, so if you work through that, so h, if I added a j on the right-hand side of h dynamics, so add some j of t, right? Then I can play this same game with the response, right? So I can do so h perturbed is h plus dh dj times what was the perturbation? Well, it's going to be, so delta perturbs the dynamics through square root of n over p minus square root of n over p times, we'll have an x0 vector times delta 0. Right? And then this, I need to now compute the correction back to delta 0. Right? So delta 0 will be 1 over root n x0 times this first term, which is the system without this new node, and then plus basically this correction. So this square root of n cancels the square root of n, so I have 1 over p x0 dh dj, right? x0 with a minus sign from this minus sign, and then dt prime. Okay, so this will be the random noise part, and then this should concentrate by the law of large numbers effect, right? So then, as before, we have this single side equation for delta 0, where delta 0 looks like, we can call it u sub delta of t. This is Gaussian, or I can call it, so this is the random Gaussian part for this variable. And then plus, now what is this thing going to converge to? So this thing is a sum over n random variables. It's a trace. So once I do the average, this is the 1 over p trace of dh dj. But this is a n by n matrix, so I actually kind of wanted to find the trace with respect to n. So this is 1 over p with an n, and then 1 over n trace dh dj. So this guy is the thing I want to call the response for the h field. And then this, we said we were taking n and p proportional. So this is 1 over alpha, where alpha was p over n. And then so we get minus 1 over alpha times RH times, again, delta 0. So this is the single side equation for one of the delta fields. So we just did one step. And if you want as an exercise in the problem, you can do the same thing where you add one new site for H. H perturbs all the delta fields. Those feed back. And then you get a similar single side equation for H. And then one more exercise is you can take the response functions that you get for RH and R delta. You can Fourier or Laplace transform them, and then recover the Marchenko-Pasteur law. So that's like a nice problem. Okay, so we're going to talk about, we're in a workshop about scaling neural networks. So let's actually talk about neural networks. How much time do I have? It's still
Oh, you're until 35.
35. Okay. Yeah. So let's talk about neural networks now. Actually, are there any questions at this point? Does this kind of make sense? No? Okay. So let's define sort of a deep MLP. Let's just start with a deep MLP. So I'm going to use so Mufon mentioned the maximal update parameterization, or the principle of like how do you set things up so that the inner features move by order 1. I'm going to adopt that parameterization convention. So one way to do that is in the output layer, you can downscale the output. Instead of square root of n, you can put a 1/n here. And then I'll include an extra just variable that I'll call gamma, which is just an order 1 output multiplier that's like a knob that we can consider as a parameter. And then I'll have w for the last layer, inner product with my feature from the last layer. And then the same recursion that Mufon wrote down. Okay. What we want to do, though, is we would like to analyze the training dynamics of, let's say, gradient descent on all the weight matrices. So unlike the cases that we just considered where you had one frozen random matrix and you were considering time-varying signals to those matrices, this is a bit more complicated because now you have these signals H that are time-varying. They'll change, right? If I'm actually doing feature learning, they're going to change over the course of training. But the weights are also changing, right? So everything's kind of a function of time. And so what I'm going to try to present is a way of sort of isolating the random part, sorry, the random initial part from the dynamics. So let's say we did like, let's look at SGD training. Okay, and what I'm going to do is I'm going to introduce, at every time step t, there's a mini batch, let's say, BT, which is a set of all, set of data points, x mu, such that mu is used in the mini batch at step t. Okay, so what I do is I construct an iteration procedure on my weights. And if I do the scaling correctly, right, the right scale, well, I'll describe it in a second. So what I'm going to do is, so WL t plus 1 will be WL of t, and then plus eta gamma over square root of n. So this eta and this gamma are both order 1 numbers. And then I'll sum over all time steps t prime less, or sorry, I'll just say sum over the mini batch BT, so x in the mini batch here, BT, of 2 functions, so g of x in layer L plus 1. So I'll define this gradient. This is basically like a back-propagated gradient signal that I'll define in a minute. And then there's a forward pass that's just the features that we've been used to. So 5HL of x, okay. So you get a bunch of spikes, right? So the matrix looks like at every step, I get you know, a rank, some rank mini batch size, potentially sum over outer products of gradients and features. And the gradients are defined as n times gamma, so that's to kill this factor, and to make this order 1, times derivative of f with respect to h in layer L. Okay, so this thing, when you do this rescaling, all the W's are order 1. So this backward pass makes sure that this G has GI's sort of unit entries, just like the HI's in Mufon's forward pass. Okay, the backward pass equation, you can actually express it in terms of the weights, right? So you just do chain rule, or like back propagation. So there's a rule that you'd get that GL for each data point would be 1 over square root of n, or let's write it like this. So it'd be the derivative of the activation at that layer, element-wise multiplied by 1 over square root of n, W L transpose GL plus 1. Okay, so if I knew G in the forward layer, I go backwards kind of through the transposes of the weights. So that's the normal backprop rule. Okay, so the question is, under what conditions can this dynamics on the weights and the forward pass and backward pass dynamics on the H's and the G's, in what sense can I close them and verify that there's like an infinite width limit that makes sense? So that's what we want to try to do. Okay. So what we want to do is basically try to look at how the H's are evolving under the dynamics on W. So what I can do is I can just say, hey, well, expand the forward pass condition. Right, so I have this HL plus 1 of x is 1 over square root of n times WL 0. Right, so that's the initial condition part, times the feature at layer L at data point x. Oh, and this is at like time t, let's say. Okay. So this is the part from the random initial part, and then I need to accumulate or add up all the kind of corrections I got from my gradients. Right, so this is plus eta gamma over n, because there's a factor of square root of n and then a square root of n over there. Sum of t prime less than t, sum over the x's in the batch at time t, of GL plus 1 of x. And then I have an inner product, phi of, well, I should probably use x prime here. Let's use x prime. This is distinct. X prime, and this is at all times t prime, dotted into phi of x comma t, right? So the feature phi of h on data point x at time t. Okay, so this vector and this vector, for example, if they were uncorrelated inputs, this could be of size, it's a sum over n things in the same hidden layer. So this could be, h of x prime t prime. This is order n, and I actually want to introduce a variable, which is, let's call it c phi of x prime t prime. And this is going to be 1 over n phi of h xt dotted into phi of h x prime t prime. Okay. So this is like a correlation function. It's like the correlation functions we've seen before, but now there's not just a time-time correlation. There's also like a data point correlation. Okay? And okay, so now this is the forward pass kind of dynamics on H, written in terms of the random initial part and a bunch of feature correlations. So this whole thing, when I absorb this n here, so I have 1 over this thing over n, this inner product is this C phi function. Okay? And then I can do the same thing for a backward pass. So let's define this variable that's linear. So let's disregard this, and let's write this variable that's linear as z, zl xt. And I can do the same thing. So zl xt is 1 over square root of n wl 0 transpose. And then I have this eta gamma. It's going to be a sum over t prime less than t, sum over all the x prime in the batch at time t prime. And then it's going to be phi of hl x prime t prime. And then I'm going to call it c sub g. This is the gradient correlation at the next layer up. Okay. So now at this point, right, we have everything in terms of correlations of features, so phi, and correlations of gradients. So the CG is 1 over n g dot g, right, with all the indices. To simplify the notation a little bit, let's introduce a superindex A that's like data point. So we could have like x mu and time t, right? So this is like This is like a joint pair of things. We could group together the data point and time indices into a super index, right? So we could write CAB is like GAGB, and we could write C phi is phi. So the point is we have a bunch of correlation functions, and then we have these random matrices, right? And one random matrix is going kind of forward through this WL0, and one signal is going backwards. So this actually is a lot like the bipartite calculation we just did with the linear regression, actually. And so the claim is that as n goes to infinity, what we would like to show is actually that these things decouple. So each of these terms breaks up into a colored noise process plus a integrated response, right? And so if you trust me on the examples we've done so far, which I know were like maybe a little simple and a bit tedious, these will have the following description. So the claim is that at infinite width, when I take the width of this network to infinity, as n goes to infinity, all the neurons hi of t, they all become IID. They're all IID draws from some limiting measure mu of h. And all the g's or the zi's of t's are also drawn from some limiting measure. Okay, and how do I define those distributions? Well, I have a single side equation that breaks up into one term that looks like a, I'll call it u sub h, L. So this is a Gaussian process, right, with this colored cross-correlated covariance that we talked about before. And then plus we'll have like an integrated correction, or like a sum over all the corrections. So for all, let's use this xt. So A is this xt combination thing. So HA, UHA will be a sum over all B of, I'll call it R phi for the one layer back, times GB, plus this eta gamma sum over all B that are admissible of G. Okay. I'm sorry, I realize I dropped one thing in this update. There's also just an error at the output for this data point at this time. So this error at the output delta is the derivative of the loss with respect to the function on that data point. Okay, sorry. So that's one more term here. But the point is that's just modifying this this expression. So there's a delta here in this equation, a delta here in this equation, and a delta B. Okay. So every neuron decouples. Each neuron is independent. The neurons produce sort of correlation functions that I can get as averages. So how do I actually calculate C phi AB? It's actually the average just of phi of HA, phi of HB, where the average is over this GP, effectively. And then the Z dynamics have a similar form that are also coupled to H. So ZA will break up into a random part, a response part, and a correlation part. Okay, the structure of the equations is not so important, but the point is that this is actually, the dynamics at infinite width are actually resembling this kind of like DMFT object. And all the correlation and response functions that govern the output dynamics of the model are converging to some well-defined average over this process. So you have like a stochastic process that decouples over neurons, averages over the neurons in the population, sort of control the effective macroscopic dynamics. Are there any kind of questions about this this result? Or maybe I could state it more clearly. But basically, the claim is something like, at a high level, is something like the following. So we were interested in this question about scaling limits or infinite width limits. And then the result was as you take the width to infinity, the network output function, right? So that's controlled by this last layer thing, right? It'll also, you can do this same DMFT analysis for this output function. And in discrete time, f of xt can be written as a sum over all t prime less than t, sum over all x prime in the batch, times two terms. So one term that's a response function for the last layer across x prime, t prime. And then another term that's what you naively get just from updating the last layer weights, right, which is sum over t less than t prime, sum over x prime in the batch of delta okay. So the claim is okay. So so where this R5 function and this delta function this is C phi x prime t prime. Okay, where R phi L and C phi L are deterministic solutions to a DMFT, to a system of DMFT equations. Right? So solving these R's and C's requires actually solving for the R's and C's at every layer. So there's basically a joint collection of variables. So for each layer, there's a C phi L, a CGL, an R phi L, an RGL. Okay? And if I know all of these, then I actually can control the output of my neural network. So I can say exactly kind of what the neural network converges to. And it turns out you can, from these equations, what's kind of fun is you could ask what happens as gamma goes to 0, or when gamma goes large. So what you can show is that actually gamma going to 0 recovers the NTK dynamics, where basically the features don't end up moving. You can kind of see that from the structure of these equations. But the output of the function, the output of the network still moves. And if you take eta to 0, you'll also, with some number of time steps diverging, you can get the gradient flow version of this, which is sort of nice. Okay. One last thing I want to describe is sort of a newer result. So these sets of equations describe kind of what the data point by data point correlations and time by time correlations inside the network during SGD look like. We were kind of curious about, is there any interpretation of the weights, right? So how the weights are updating. And one problem, so we wanted to ask, for example, does feature learning ever induce sort of outliers or spikes in the matrices? So it's sort of from these equations for the weights, it kind of looks like you get some initial part plus a bunch of low-rank spikes. So we were kind of asking, can we say something about the structure of the spikes? So let me do just a simple warm-up example that's kind of fun, which is a spiked Wigner, where we can learn a quick trick. Or a spiked GOE. Okay, so let's say my matrix M was this random part. So this is the random symmetric GOE matrix, plus a bunch of low-rank spikes. So let's say I added something gamma over n, a equals 1 to n, VA transpose. Okay, so this is a symmetric spiked matrix. Okay, these VAs, let's assume these VAs have correlations. VA dot VB is sigma VAB. Okay, so let's study the evolution of a linear probe. So let's introduce a linear probe as before. So I can do DDT of H on, let's say, M times H. Okay? So I can break this up into 1 over square root of n AH plus gamma sum of, let's say, A of VA 1 over n VA dotted into H of T. Okay. So we're going to study the system at large n. We can assert that this is sort of some kind of correlation function. We can call this CVH T subscript A. Okay. And now what we can try to do is we could try doing a DMFT. So this should be self-averaging. We can try doing a DMFT over this random capital A matrix. And so if you do that, you get the same kind of single site equation as before. plus this. Okay. So now we're interested in, oh, and we can assume that the correlations start, so H starts off potentially partially correlated to the VHs. So we can assume that at time 0 there's some CVH at time 0 is some vector C0, right? That's in the dimension of, oh, sorry, this is not N. Sorry, I'm so sorry. This is S. So we're going to assume S is order 1 with respect to N. So the number of spikes is not diverging with N. Yeah, apologies. Okay. Cool. And and we have some initial condition for the alignment between this H probe and the V's. Okay. So we can compute within this DMFT the kind of correlations between H and V and write down a differential equation, right? So dCVH of T is like this dt prime r tt prime CVH T prime. Let's say sub A. We're going to do this as a vector even if we want. So it's a vector over the spikes. And then we have here, we'll have the sigma matrix, which is this sigma V matrix, acting on this C V H T. Okay. So let's do the same Laplace transform trick, right? We know the response here is TTI, right? So we know this is just a function of T minus T prime. So I should be allowed to do a Laplace transform. So plus gamma sigma V C of Z, and then plus the initial condition is I could view that as a Dirac delta function, d of t, right, times C0, which under the Laplace transform would just give me a constant term. Okay, so what is this saying? This is saying in Laplace space. In Laplace space, I have C of Z is Z minus R of Z minus gamma sigma, right? Inverse acting on C0. Okay, so the poles, so this is a linear system, and the poles here should tell me about like kind of the long time exponential modes that I could have in this system, right? So if I imagine that C of t was dominated by some E of zt for large t, the maximum of this should be actually telling me about the maximum eigenvalue of this M matrix. So there's a question about does that actually exceed the bulk of that semicircle law or not? So let's ask when does this have a kind of pole? That could be a potential exponential mode. So we could have candidate outliers by looking at the condition, the secular equation Z minus R of Z minus gamma sigma equals 0, right? So those are potential things. So notice this is not the, it's sort of like a normal eigenvalue problem where you'd look for what Z's are eigenvalues of sigma, but actually there's this extra nonlinear function from the random part. Okay, and so we could diagonalize, we could say that the spectrum of this matrix is a bunch of lambda sub a's. And then this breaks up into a bunch of different separate conditions, right, that are like Z minus R of Z minus gamma lambda equals 0. Okay. And then we had this equation from the beginning that ZR was 1 plus R squared, right? Or we could write this as R is 1 over Z minus R. Right, so this is Z minus R. So this is 1 over R. And this is the candidate Z sub A, right? So this is some Z sub A. So the condition for Z sub A is 1 over R is gamma lambda, right? And now I can say, okay, well, plug R is equal to gamma lambda back into this equation, right? So ZA is equal to 1 over R, or so sorry, it's R, which is 1 over gamma lambda A plus gamma lambda A, okay? And we're interested in roots like this that exceed 2, right? Because we need to be outside of the semicircle. And this is exactly the kind of classic BBP transition. So each of these Okay, so when does this exceed 2? It exceeds 2 when this gamma lambda equals 1. So if gamma lambda exceeds 1, then all of a sudden, instead of being trapped inside, we promote an outlier eigenvalue. And so we can see if we have a rank S matrix here, depending on the scale of these eigenvalues, I could have up to S outliers. Okay. So what gets in the way of doing this for neural networks? So like, let's say I had a weight matrix like that. What makes it hard to study the weight spectra of trained neural networks, or like neural networks during optimization? Okay. The thing that makes it challenging is that the W's, so I have something like WL of t is WL of 0 plus, let's just do a sum over like this superindex again, and we have this GA, and then this phi A. But the problem is that phi A vector is some element-wise, so the DMFT equations just show that there's some element-wise function, phi sub A, that takes in all of the random vectors, so let's introduce the following. So it takes in a bunch of random vectors chi b for all b. And g sub A is a function little ga of a bunch of variables that I'll call chi b. Okay, so where these functions act element-wise on vectors, and what are these vectors? So these vectors are chi is 1 over square root of n w0, so the initial part acting on each feature. And psi A is 1 over square root of n w0 acting on the gradient. Okay, so we had basically a bunch of time-varying features and features on different data points. We had a bunch of time-varying backprop signals. We had the forward dynamics through W0 that were altering the G dynamics in the next layer. And we had the backward fields through the randomness that were affecting this feature. So this is structurally the kind of problem that we were looking at. But why this is harder than the classic BBP is that the spikes themselves, right, they're functions of the random matrix through these projections. Right, so I need a way to kind of like, to solve that problem. Okay, I'll write down the result, and then that's not going to be, it won't be like so intuitive, but then I'll give a toy example that modifies this problem, where you can learn what's going on. Maybe I'll just, yeah. So the secular equation that you need to solve, when you include these, the fact that there's an endogenous dependence of the spikes on the random matrix through the projection, it ends up giving you, it doubles the size of your secular equation that you need to solve, basically. So here's the result. This is from a new preprint. Okay, so the singular values of WL of t in the infinite width limit of training, the singular values of WL of t in the infinite width limit are determined by a zero determinant condition, where A is equals 0, where A of z is a 4s by 4s matrix. So S is the spike, so the spike count, so how many potential updates I had here. So it could be batch size times steps, for example. And A has the form the following. So it's G of z inverse 0 minus R phi. So we had this response function phi, C phi minus C phi. Then we add 0 G of z inverse R phi transpose minus R phi transpose minus RG RG transpose, 0, where G of z is the resolvent of a Wishart. matrix of the random initial part. Okay, so my point is I wanted you to get the idea that this is similar in spirit to the kind of secular equation that we had here for outliers. But naively, if you did the calculation, assuming that the random part was independent of the spikes, you would get a 2s by 2s system. But in fact, you get twice as big of a system when you do the DMFT properly. So in the remaining minute, I'll just give a toy model, but it's in the homework. You can do it if you want. That captures the same phenomenology, but you can really understand what's going on in an easy way. And so this is a two-level system. So I have a matrix that's dynamical. So I have mn plus 1 is mn plus, at every step I add some vector vn. Okay, and vn has its own dynamics that depend on, let's call it eta. Let's add eta times m sub n vn. Okay, so now this is sort of structurally similar to the problems that we were getting in the mean field infinite width limits. We have a time-varying matrix. The matrix is being updated with spikes, but the spikes themselves inherit dependence on the matrix itself. And the matrix starts, M0 is GOE. Okay, so what you do is you try writing down a fictitious field again. You do m sub n of h. You expand m as the sum of all the spikes. And then unlike, let me see, did we get rid of that? Oh, okay, I guess I erased it. We had if you do the problem correctly, you get a modification to the secular equation. So introduce, so sigma would be, again, 1 over n VA dot VB, or VN dot VM. And you have an R in M, which is some response for V. So you have these matrices, sigma and m. And now you can write down the secular equation for this system in terms of sigma and r. So it's z minus r minus, let's call it, you wanted g of z minus this rv minus gamma sigma. And then minus sigma v. And then minus gamma r transpose. And then z minus RV transpose. Okay. Okay, so my point is, just like, so in this problem, so if I had assumed that the random part of this matrix was kind of independent from the spikes, we just had this kind of term without this RV. Adding this coupling introduces this new term in the upper block, and it also introduces like 3 more blocks to your secular condition. So my point is DMFT is very flexible. How do you actually get this? You can just analyze this 2-level DMFT where you properly treat the couplings and correlations between V and H. And if you properly do that, you sort of get some extra terms, and you can actually accurately track outlier dynamics in these systems. So it's sort of a method that we're trying to now push to even these time-varying matrices. So you have a random maybe part of the matrix, but you have a time-varying component of the matrix, like what you have in neural networks. You have closure at the level of the dynamical features, like the features that are being driven by the matrix, but you also can get closure at the level of the spectrum of the matrix through time. So that's this newer thing that I was presenting. And so this is kind of these this regime at the moment is really useful for low-rank spikes, but I'll talk a bit about a future direction where we can do work toward extensive rank analysis where the number of spikes becomes comparable to the dimension of the space n. Are there any kind of questions about this? I guess I'm out of time. But.
Yes, sir. Big questions, we would just like to thank the speaker. Just come back to the questions.
So the result about the singular values of the weight matrix, so is that assuming SGD or at the start of this?
Yeah, that's a great question. So at the moment, these equations are for SGD, so the kinds of updates I have here. I think it would also, in this regime where the batch size is order 1 compared to width, you could apply it to things like normalized SGD or muon, which has a a simple thing. But Atom, the per component nature of Atom, I think maybe messes up some of the spike statistics here.
Yeah, I guess what I was going to say is if you applied it, say, directly says all the singular values in your data 1, does that
Well,
directly start?
okay, so this is a good point. Yeah, this is a great point. So technically, right, so it depends on the regime you're in. If you're really at infinite width, and the batch size is order 1, mu1 has like a deterministic effect within these equations. But then if you're in the opposite limit, where like actually batch size is much bigger than width, then it really, there's no null space. And actually I am perfectly whitening the gradients. So it depends on whether like the number of spikes is kind of comparable to the width, or whether the width is like really infinite compared to the spikes. So this machinery was kind of in this super wide regime where like everything was sort of held order 1, data and time was held order 1, and width was diverging. We'd like to go beyond that and look at maybe some of these proportional asymptotics that Mufon mentioned, where maybe data or batch size are comparable to width. At the moment, I only know how to do that in linear networks, where you can do proportional data, width, and input dimension kind of diverging proportionally. At the moment, it seems kind of difficult to do in nonlinear networks because you have to go beyond this regime. I will say, like in experiments, the super wide limits seem to be performing better than like making the thing narrower doesn't make it perform better or something. So like wider tends to be better once you parameterize properly. So in some sense, this is like calculating the optimistic asymptotic limit.
Right, so we've just got to one question, sorry. But maybe it might get you to speak afterwards. That's all just yes.
I was just gonna clarify slightly that so when you write down that equation of determinant of A of Z is equal to 0, because we're trying to solve for G from this equation.
Oh, sorry, I'm so sorry. So G is known. So G is the bare part. It's like the resolvent of the matrix without any spikes.
I see.
And then the spikes are potential candidates Z. So I'm looking for Z's that solve this equation. But Z shows up both in the G of Z and this thing.
I see. And then when you do solve for Z's that show up, and these are exactly where the spikes are.
Yeah, exactly. So I can show some plots if you want. But so we have some plots like so through time. You start with this Marchenko-Pasteur bulk. Let's say for your singular values free network. And then you can track like one outlier kind of merging, and over steps it kind of moves to the right. And then another one can pop out and it moves to the right. So you can see, but what's interesting about these equations that was kind of cool is so you populate these tables with DMFT order parameters. So order parameters that you've already computed, it's the R's and the C's from the DMFT. And those tend up being kind of low rank across time steps. So it's like you effectively get not as many you get fewer outliers than you'd naively expect from a bound of like just how many spikes did I accumulate. And I think it's partly because there's strong correlations across time steps and across like data points. So.